Hello guys and welcome to another video on GD&T. In this video, I want to break down the differences between coordinate tolerancing, which is the traditional way of tolerancing parts, and GD&T, which is geometric dimensioning and tolerancing. What is the difference? And I will explain that using this example. So let us take this example of an assembly. So let's say that there is a machine in which there is a panel, and that a part of that panel is this green color part, which is having a rectangular slot over here, and there is a component which is being assembled to the pink color plate using two fasteners, and the main functional requirement is that it should provide a guideway or align with the center slot. As you can see over here, this rectangular slot should align with this rectangular slot. That is the main functional requirement, and that has a certain purpose attached to it. So for this kind of a situation, for this kind of a component, what are the important functional features? So when we are understanding tolerancing schemes, we need to understand the important features which we require to be toleranced. So in this case, there are three sets of important features. One is the mounting surface, that is the surface which will be in contact with the pink color plate, that is the back mounting surface. Then there are two holes which will be used for mounting. So these two holes are important, functionally important, and then there is a center slot. The center slot, the two holes, and the mounting surface are three sets of important functional features. Now, when it comes to control, what we mean by control is how are you going to control the variation of the features in manufacturing such that they are accurate to the design and they perform the function as required. So that is what we're talking about control. So one aspect of control is the form of the mounting surface. That is one important aspect of control. What do we mean by form? Whether the mounting surface is flat or not, whether it is having a straight surface, or whether there are undulations, or the part can rock. So that is form of the mounting surface. Second, the orientation of the mounting holes to the mounting surface is important. The holes have to be perpendicular to the mounting surface. If they are at an angle, then when the fasteners are being inserted, then they will not be we will not be able to fasten this part with respect to the back plate if they are at an angle. So that is also important. Not only angle, the center to center distance between the two holes is also important. That should match with the center to center distance on the back plate. So that orientation and position both are important. Mounting hole center distance, that is what we're talking about, mounting hole center. Then there is geometric relation between the mounting holes and the center slot. So when we are locating this part based on the mounting holes, then the position of this slot with respect to the mounting holes becomes very important. Now let's say if you want to make a manufacturing drawing of this component using the traditional tolerancing method, which is a coordinate tolerancing, which is plus minus tolerancing. If we make a drawing based on that for manufacturing, it would look something like this. Of course, there can be different ways of creating the same drawing. This is one way of creating a drawing for manufacturing, and which is capturing the major controls which we had spoken about earlier. So you can see that there is a dimension for the holes, the size dimension 2x 10 plus or minus 0.1. Then we are locating the two holes based on a point on the part, which is this point over here in this drawing. So we are taking a reference point on the edge of the component, and then we are locating the holes based on that edge. So from this point we are locating these two holes. So the location of this hole is 18, 20, and this hole is 52, 20 with the location or position tolerances given over here, plus or minus 0.15, plus or minus 0.1, plus or minus 0.1. So this is how the holes are being located using a point. Then from that point we are locating the position of the rectangular slot as well, which is the keyway, which is having a width of 20 and a size tolerance of plus or minus 0.1, and the location of the width, the start of the width is 25 plus or minus 0.1, and the depth is 5 plus or minus 0.1, and the width of the component is being controlled over here 15 plus or minus 0.1. Very important disclaimer over here, these tolerances are just for indicative purpose, just for demonstration. They might not be accurate as per the ISO standards. They are just to indicate or demonstrate the concept. If we analyze this drawing and try to answer the questions of whether it is controlling the important functional features correctly or reliably or not, then we will see that there are various issues. What are the issues? There are multiple issues with the drawing. First is there is no explicit form control of the mounting surface. So as we have seen, the mounting surface, the surface which will be coming in contact with the back plate, the pink color plate, that form, the shape of that surface, the flatness is important. Here we are not controlling the form explicitly. There is no explicit control of the form, but through rule number 1, which is a Taylor's principle, we can say that form is being controlled, but form has to be perfect at maximum material conditions. So there is a rule number 1 called as a Taylor principle, which says that for a feature of size, which is this, a width, the size when it is at its maximum, an external feature of size, when it is at its maximum, that at that maximum size, that is maximum material condition, it should have perfect form. So that is a default control of form, which basically means that if the size of this width is smaller, the form can vary a lot, and that can be detrimental to the function. Second point is the holes. These two holes are being located with respect to an arbitrary origin point. So this point is not of functional importance. It is being located with respect to that point on the right corner, and dimensions are originating from there and tolerances are applied to that. Another point is that the dimension 25, this dimension is locating the start of the slot from the edge, but it does not say anything about the center plane of the slot. Whether the center plane of the slot has to be centered based on the mounting holes or not, there is no information regarding that. So there is no control regarding the centering of the slot with respect to the mounting holes, because the part is being located based on the two holes. Then the slot, that is this key, has to be centered based on the mounting holes. Then it will align properly. There is no information regarding that. There is no explicit control on the orientation of the holes as well. The holes and the slot, there is no control of orientation of the two features of size, which can be detrimental to the function as well. Now if we have a look at the GD&T drawing of the same component, considering the same important functional features, here is the GD&T drawing. So let's go through one by one. First, let us have a look at the primary datum feature. Where is the primary datum feature? The primary datum feature is A, that is the mounting surface. The mounting surface is given as a primary datum feature A, and that primary datum feature surface is being controlled in flatness within a tolerance zone of 0.05. The width is intact, but this width does not control the form. So this flatness control basically overrides rule number 1, that is the Taylor's principle. So that is the first point. So then we are controlling the flatness, the shape or form of the mounting surface. So that is one benefit of GD&T first. Then if we look at the secondary datum, the secondary datum has been applied to the pattern of two holes which are having the size of 10 plus or minus 0.1, and they are being controlled in their perpendicularity with respect to datum A. That means the holes, the two holes, should be perpendicular to the mounting surface. So this is controlling the perpendicularity. The issue of orientation is being resolved over here. That should be within a tolerance zone, a cylindrical tolerance zone of 0.1. So this is datum feature B. Datum feature B is a set of two holes which is a feature of size. Now, which are individual features of size. Now let's have a look at datum feature C. Datum feature C is the top surface. This top surface is being controlled with respect to perpendicularity with respect to datum A. Again, this top surface is being controlled in orientation with respect to datum feature A, that is the mounting surface. So we have relation of orientation of holes with respect to mounting surface, and also the top surface with related to mounting surface, and that is a perpendicularity control over here. So these three are primary, secondary and tertiary datum features. Now let's have a look at the a position control which has been applied on the slot. So on the slot, which is having the width of 20, which is a feature of size, there is a position control which has been applied, and which says that the position should be within a tolerance zone of 0.2 with respect to datum A, B and C. So with respect to the datum reference frame of A, B, C, we are controlling the position of the slot. That is, the position of the center plane of the slot is being controlled. And that is basically being controlled with respect to the positions of the two holes. So wherever the holes are positioned, we are not worried about the position of the hole from this point. We are saying that wherever the holes are positioned, the slot should be centered based on those two holes. That's what we are saying through this feature reference frame, this setup. And additionally, we are applying a parallelism control on this surface, which can aid in the alignment of the keyway with respect to the slot on the mating part. So that is a parallelism which has been applied. So this surface has to be parallel with respect to the top surface, which is datum feature C. And there are basic dimensions which are applied. So this 17 basic dimensions is between the slot center plane and the axis of one of the holes, and this 20 basic dimension is originating from the hole and locating this top surface, that is datum feature C. So there is explicit form control on the mounting surface through flatness. First point. Second point, the orientation of the two holes is being controlled with respect to the primary datum feature. The two holes as a pattern are datum feature B. The top surface is datum feature C, which is again controlled in its orientation, which is this. The position of the slot is controlled with respect to the holes. We are controlling the center plane of the slot with respect to the holes, wherever the holes might be, because the main functional feature is the holes, because they are used for mounting. And so the slot has to be centered based on that. And parallelism is also applied, and rest all dimensions and tolerances are the same. So you can see how applying GD&T has made the drawing so much better and conveying so much more information, and we are able to control the functional features so much better and in a very unambiguous way. Of course, this can add a lot of cost when it comes to inspection, because there are so many other inspections which have to be done, like parallelism, perpendicularity. These can add cost, but if the functional requirements are stringent, then a GD&T drawing is always better as compared to a traditional tolerance drawing or coordinate tolerance drawing, in which the control, the geometrical control of the functional features has to be very tight. Thanks a lot for going through this video. I hope my point has been made regarding the usefulness of GD&T as compared to coordinate tolerancing. I am making many such videos on GD&T and tolerance stackup, and I hope to influence your learning journey through my videos. Please do like, subscribe and share this channel. I hope it will be useful resource for design engineers all around the world. So thank you.